All right, let's take a look at the designing your own experiment. If you're having some problems or you just are tired and need a little guidance on this. So it says, you've learned that when you add a piece of hot metal to cooler water, that the energy released by the hot metal is equal to the energy absorbed by the water. When this experiment is done in an ideal calorimeter with no heat energy leakage, your measurements will allow you to perform these calculations and get some pretty good results, much better than if we were doing this in person. So for this assignment, we're going to ask you to design your own experiment and carry it out with this simulator. So click on that to have that ready to go, and it'll be the experiment tab, run experiment. All right, so the question that we're being asked in this lab is, when a hot piece of metal is added to cool water, does a metal with a lower or a higher specific heat value increase the temperature of the water more? So first you need to write your own hypothesis. Um, I wrote mine, and just to save time, I typed it out ahead of time. If a hot piece of metal has a higher specific heat, then I think it will increase the temperature of the water more, because metals that require more energy to change temperature also release more energy to change the temperature. Okay, that was my theory at least. So then let's figure out what metals we're going to use. So we want a metal from this simulation that has a low specific heat and one that has a higher one. So kind of a cool thing when you're doing this, oops, you want to go to solids. Um, you can click show specific heat to kind of figure out which ones you want to use. So 0.217, maybe these go lowest to highest until you get to the unknowns. Oh yeah. Now I'm going to use tin, which is 0.217, versus aluminum, which is, let's check out what aluminum was, 0.903. Okay, and I guess it's hard to get everything to fit. So let's keep the mass the same. Actually, we'll do tin first. So we'll do 50 grams, and let's max out the temperature. So we're going to do 50 grams, 200. You get to choose whatever numbers you want for yours. I'm going to do 100 grams of 20 degrees Celsius water. And then for the aluminum, it'll be the same, 50, 200, 120. We want to keep those variables constant. So, all right, let's get ready to run the experiment. So we're doing water, and we're doing a mass of 100, temperature. Why not show the specific heat? And next, show the graph and the microscopic view. Here we go. So the tin, the hot tin is being added to the water, and you can see the water is heating up, the tin is cooling down, and this will keep running until they reach equilibrium, till they're at the same temperature. So the water started at 20. We're really interested in seeing the final temperature, how high the water, or what the temperature increases to, 24.55. So the tin went down from 200 to 24.55, while the water went up in temperature from 20 to 24.55. So let's do that same experiment, only let's run it with aluminum. So aluminum, 50 grams. Oops, we did 200. Okay, and then we did water, 100 grams, temperature 20, sure. Let's show the graph and the microscopic view. And you can really see here the metal and the water. As the water molecules come in contact with the metal, they're turning brighter red. That is showing that they are increasing in temperature. And look, the water is increasing more when the metal has a higher specific heat. So I'm kind of already answering my question. So 37.53. All right, let's do some math. Show your work for calculating the amount of energy absorbed by the water when the metal with the lower specific heat value is added to the water. So we've got Q equals mass of the water is 100. Specific heat of water, I know we changed the number like 4.19, 4.18, 4.2. It's 4.184 in this simulation, joules per gram degrees Celsius. And the change in temperature, it went up from 20 to 24.55. So it went up 4.55 degrees Celsius. I'm wondering if I should add a column of the change in temperature. No, it's fine. All right, so I'm going to plug this into my calculator. So we get a value here, 100 times 4.184 times 4.55 equals 1,900 approximately joules. I'm going to round that. And then let's do the same calculation. It's still a mass of 100 grams of water. The specific heat of water never changes. But this time, the temperature went up from 20 to 37. That's 17.53 degrees Celsius. So 100 times 4.184 times 17.53. That's 7,335 joules. So now I'm going to write my conclusion. So first, answer the lab question in a sentence. When a hot piece of metal is added to cold water, does a metal with a lower or higher specific heat value increase the temperature of water more? When a hot piece of metal is added to cool water, a metal with a higher specific heat value versus lower specific heat value will increase the temperature of water more. Site-specific data. I guess I should really have phrased this in a different way. Sorry, I'm going to change this up. When a hot piece of metal is added to cool water, does a metal with a lower or higher specific heat value result in a larger absorption of energy by the water? If this metal has a high specific heat, then I think it will cause the water to absorb more energy. Okay, there we go. I just wanted to make that make sense. Well, so that we use the data that we calculated. When a hot piece of metal is added to cool water, a metal with a higher specific heat value will result in a larger absorption of energy, of heat energy by the water. So our evidence here is that when tin, which has a specific heat of 0.217 joules per grams degrees Celsius, was added to water, when, let's get specific here, when 50 grams of 200 degrees Celsius tin was added to water, the water only absorbed 1,900 joules of energy compared to when 50 grams of, oops, the metal with the higher specific heat value, comma, aluminum, specific heat equals 0.903 grams degrees Celsius. The metal with the higher specific heat value caused the water to absorb 7,335 joules. It should be noted that the same amount of aluminum was used and it was also heated to 200 degrees Celsius to keep those variables constant. This isn't my most concise conclusion here. Okay, but now we're going to get to the reasoning. This makes sense because the higher specific heat value means that each gram of aluminum can release 0.903 joules of energy as it decreases by 1 degrees Celsius, while tin can only release 0.217 joules of energy for each gram of it as it decreases by 1 degree Celsius. That's the chemistry behind it. We haven't learned specifically why. For whatever reason, still unknown at this point in our learning, aluminum is more efficient at releasing energy than tin. There we go. I feel like that was more painful with my switch in it, but hopefully that helps you out.